It's 2 o'clock in the morning. A policeman is sitting by the side of the road and sees a Chevy Malibu driving down the street. The Chevy Malibu is, first of all, it's in the gutter, then it's crossing the yellow line, then it's in the gutter. The policeman pulls over the Chevy Malibu. The driver of the car appears to be intoxicated. He takes, her name's Mary Anderson, he takes Mary Anderson to a medical laboratory. This is a hospital. And at the hospital, the medical people draw a blood sample. They fill up 2 tubes with blood from the defendant. They put the tubes in a special kit, sign them and seal them and put them in a special kit, and send them off to a medical laboratory. The medical laboratory opens the kits, along with others, opens the first tube, takes 10 microliters exactly out of the tube and subjects it to chromatographic analysis. The chromatographic analysis gives a response to the ethanol of 11.5. Against that day's calibration curve, the 11.5 gives a value of 128 milligrams per deciliter, or 0.128% blood alcohol. So, analysis produces errors. You could say, but how do they know what it really was? Well, the truth would be that they don't know what it really was. If the blood alcohol was run again, it almost certainly would not give 0.128. If it was run a third time, it would probably give a third different value. The laboratory technician that ran Mary's blood has been running controls at very regular intervals for days and months and years and maybe even decades. She's got a lot of control data. The control values are put into a distribution curve, and a standard deviation is calculated on the control values. There's a couple of assumptions that are made. The first one, there's 2 assumptions. The first one is that the control samples are treated like samples and really are samples. They are samples. And the second assumption is that the standard deviation on the controls, the standard deviation will be the same no matter where the control was run. So, how does this apply to Mary? The standard deviation of the controls is her standard deviation as well. So the variation in the controls is the variation in Mary's blood alcohol as well. Okay, so Mary Anderson has a 0.128% blood alcohol. We have a standard deviation which is calculated by a computer. We have a standard deviation of 1.1, which means that there's a 68% chance that her value is between 0.129 and 0.169. And there's a 95% chance that it's between 0.1258 and 0.1302. So there's errors in the analysis. We know there's errors in the analysis. We also know that the errors are, in this context, not significant. So what is Mary's blood alcohol anyway? The statute in most states is 0.1. So that's 100 milligrams per deciliter. 0.100% blood alcohol, BAC it's often referred to. Is her blood alcohol less than 0.1? No, there's no possibility of that. Is it less than 0.2 0.12? No, not really possible. Is it less than 0.126? Yeah, it could be. This is very common in analysis. Analysis is usually used to establish a criteria. It's usually used to determine limits within a criteria. Analysis is used to answer a question, yes or no. Does this fit the specs or does it not fit the specs? Is this more than a certain level or less than a certain level? Mary Anderson is pulled over for drunken driving and she has a 0.128 blood alcohol. Okay, she's over the limit. Suppose she had a 0.148. Doesn't make any difference. Suppose she had a 0.118. Doesn't make any difference. Suppose she had a 0.108. Now she's up close to the limit. Well, then there might be a gray area there. Analysis is for things like in the environmental business. If it's more than 5 parts per billion benzene, then you got to pay attention to it. If it's more than 50 parts per billion, then you really need to keep monitoring it. If it's more than 100 parts per billion, you need to bring in the earth movers and start cleaning it up. For example, the salt concentration in a snack food, it has to be between 1 and 1.8%. I used to work in a medical laboratory. Lithium has to be between, the doctors want to see a lithium level between 1.3 micrograms per milliliter and 15 micrograms per milliliter. The windows are typically really big. Okay, so let's go back to benzene. Let's say you have a benzene level that's 300 parts per billion. 300 parts per billion, flags go up all over the place, the consultants are brought in, the earth movers are called, the construction companies are called in. Okay, let's say it was 500 parts per billion. Doesn't make any difference. If it's more than 200, then you have to look at it. Most analysis is like that. In most cases, errors are not a big problem. And there's no reason to be all freaked out about them. Analysis produces errors. The world is not a cut and dried situation. The limits themselves are typically, like in the law, 0.1 is over the limit. 0.05 is driving while impaired. In most states, there's 2 levels, DWI and DUI, driving while impaired and driving under the influence. The levels are 0.05 and 0.10. Where do these limits come from anyway? I mean, I don't know. I mean, even that's not even a cut and dried mathematical deal. You got to set a limit somewhere. One last idea. Statistics is a tool that's invented by people to describe groups of numbers. I think as a scientist, as science people, or as people in general, we should be able to take these tools and use them and communicate information about groups of numbers with these numbers. I don't think we need to worry too much about them. Standard deviation is cool because it comes out in the units in which you start with. You start with percent, your standard deviation comes out in percent.